So, good morning, good afternoon, good evening to everyone. So, myself, Nilima Satyam, as a TC220 member, I welcome you all for this second lecture of this monthly lecture series organized along with the TC220 of ISMG. And it's my pleasure to have our second speaker today, Dr. Wang, who kindly agreed to give a talk. So before proceeding, so we have Dr. George. So he is a vice chairman of TC220. So and also we have Dr. Anil Joseph, who is the president of IGS here. So I'll start like I request Dr. Anil to say a few words, and then Dr. George will introduce the speaker.
Yeah, hello all. It's a great pleasure that this field monitoring in geomechanics has come out with this series of lecture every month, and it's a very informative session. And look forward for seeing you. And it's very important talk today. Professor Wang will be talking to us to a very vital aspect, the prediction of landslides. It's a very important aspect which can save large number of lives. So that's very essential in areas like India, which has got a lot of problems connected with landslides leading to numerous deaths, which is happening every year. So it will be informative, and I request all the young participants not only to listen to that, try to apply the knowledge into practice and make sure that we are improving the society's capacity of resisting the landslide in a better way, so that only few lives are lost in the process. And I wish all the very best for the event, and I would like to congratulate Nilima for coordinating the event, and all the seniors who is attending here, Samadhya sir, George Pisota, AP Singh, Tohata sir, and all who has assembled here to listen to the. Wish all the very best for the program, and hope this lecture series will continue. Nilima has done a lot of planning, and being part of the field monitoring in geomechanics along with Nilima in the TC220, it gives me a great pleasure, and we are looking forward for the major event which is to happen in 2026 when we will be hosting it at IIT Indore.
So thank you so much, Dr. Anil. So Dr. George, so I kindly request you to introduce about our TC220 activities and also our today's speaker.
Thank you very much, Nilima. I'll try to share my screen. Can you see my screen?
Yes, yes.
Well, on behalf of the TC220 chairman, Dr. Andrew Ridley, I would like to welcome you all to this event, which has been organized by Nilima. And I thank very much Nilima for the great effort she is doing in order to support TC220 activities. I would like just to give you a very brief introduction to TC220 activities. As per this date, I can tell you that TC220 is a quite young technical committee, was established a few years ago, but we have done, I think, a great number of activities which have been very important steps, in order to enhance the culture of monitoring all over the world. The most important event which has been organized by the committee was the 11th edition of FMGN, which was held in London in September 2022. It was a great success and was the first event, the first symposium organized under the control, let's say, of TC220. The next one will be in India. Nilima and her colleagues are organizing it. I'm sure it will be a great success, and I'm sure that Nilima will say something about these events later on. For the next year, TC220 will be involved in two main activities. The first one will be what has been called a mini symposium on field monitoring in geomechanics during the 7th International Conference on Geotechnical and Geophysical Site Characterizations, which will be held in Spain, in Barcelona, in June 2024. And then in August 2024, during the 18th European Conference on Soil Mechanics and Geotechnical Engineering in Lisbon, Portugal. We will have a special section dedicated to field monitoring in geomechanics. We are now organizing this event. We are trying to put together different speakers, different events, and as soon as we will have defined the program, it will be sent to everybody in the TC in order to let people understand what we are doing and trying to attend these events. Regarding the possibility to get information regarding our activity, you can refer to our website. Our website. Here you can see the link in the website, which is under progress because, again, being the TC quite new, even the website is under development, but you can find a number of information which can be very useful to everybody. And we are also trying to develop some social activity or activity on social media. An example is what our colleague André Silva from Brazil is doing. He has opened a web YouTube channel, and he is presenting a number of speeches or presentation regarding field monitoring or monitoring in general. Sorry, I don't know. There's a, okay. Okay, sorry. And this is a very interesting idea from André in order to spread again the culture of monitoring. It has also been opened a LinkedIn page. You can see here the page, so you can join it if you want. We'll be very happy to have you as a member of this community. At the moment, we are 169. At the moment, we were 80 few days ago. Now we are 169, and probably will be more in the next days. So it is again in progress, but it's something that can be very useful. So this in brief is the activity that TC220 is doing. And this lecture that Nilima has been organizing is a very interesting part of our activity. And I hope it will continue in the future with a larger number of similar events. Having said this, we can go directly to today's lecture. Today, sorry, but there is someone who is trying to call me and I cannot close it. Today, we have the pleasure of having with us Dr. Lin Wang. Dr. Lin Wang is a senior manager of geotechnical engineering at the Chuo Kaiatsu Corporation. Forgive me for probably the bad pronunciation. And he has a very large experience in rain-induced slope stability, earthquake-induced slope stability, development of slope monitoring and alarm systems. Today, Dr. Wang will present us a lecture whose title is Case Studies of Early Warning Monitoring of Unstable Slope using Tilting and Microseismic Sensor. Something very interesting. I'm really interested in listening what Dr. Wang will present us, mainly because I'm very interested in what is called early warning. And if you allow me, Dr. Wang, I anticipate a question I will pose you later. And the question is a very simple, but at the same time, very complicated one. It is, what is a real early warning monitoring? What does it mean early? Because in the past, I have been discussing many times this point with colleagues. And I'm sure you will provide us a lot of information regarding this and something that we can use in our activities. So that's all from my side. I leave the floor to Dr. Wang. So please, Lynn, you can share your presentation and you can start your lecture.
Yeah, thank you. Thank you for introduce. So I want to share my PPT now. Is okay?
Let me try to close my sharing. Why is not okay? Okay.
Yeah, thank you. Thank you, everyone. You can see this PPT now. Yeah. I'm a senior manager. Come from Chuokai Corporation, Japan. As you know, in Japan, many disasters happen, such as landslide, slope failure, and earthquake every years. So for last 20 years, I was engaged for the monitoring. And after that, so the early warning become very important things.
Sorry, Lynn. Sorry,
yeah.
Lynn. Can you switch to presentation mode? Your PPT.
Okay. Okay.
Thank you.
Cannot hear me?
We hear you, but please go to presentation mode of your PPT.
Okay, I see. Is okay?
Okay, now it's okay. Perfect.
Yeah, perfect.
Yeah, I see. So here I will introduce some case studies about the early warning monitoring of unstable snow using tilting and micro-seism sensors. So I'll be introduce two parts or two sections. First, we'll introduce the rainfall-induced landslide or snow failure. After that, the cold seismic landslide will be after we'll use the second part. Here, this research will get the sponsor from the Cabinet Office of Japan. Is that SIP. SIP means Cross-Ministry Strategy Innovation Promotion Program, come from Japan. Yeah, they first already introduced the successful early warning case of the dam site slope failures. This is carried out by our company 30 years ago. On our 30 meter high and 200 meter length cut slope improvement construction works on the national route to national route in 1990. But as you know, after construction, we find some rock mass on a dropout, and find this slope is not so good. It's not, maybe it's unstable. So after that, our company set up two cameras, and after that, use the tensometer to get the monitoring and find the danger or not. I just show the video to you. So a rock mass of 30,000 cubic meter and collapsed after installation after 40 days. So the time of collapse has been focused according to by cycle methods. Also, the focused time of rock failure. The two video on I'm sorry, I will use the two video will be set up in the right side and the left side, and catch the detail. This is the view from the left side, the upper side, on the left side. So this is very successful early warning monitoring. If we cannot do this monitoring, large deltas will be high. Yeah, this is very a dangerous situation. And how I can do the early morning? Of course, I just introduced the bicycle method. I will introduce the cycle method will be come from the creep rupture life prediction. It's come from Monkman and Great No. So in here, if the failure happens, you will be past the 3 stage. The first, you can see, this is the first primary stage. It is already showing here, and the second stage is keep the Cree rate at the constant. After right, quick increase in here. So the relationship should be described as this function. This function. If we know, we do the monitoring about the creep rate just like this, and you can get the creep rupture lifetime. This is our volume time. Yeah, just like this. And the Seism model is come from this. The Seism, Professor Seism, and a graduate from University of Tokyo in 1956. After that, he works in Japanese Japanese Railway Institute, and after that, he carried out the field test over 80 things and fix the 2 parameter, yeah, the M and the C. And he rewrites the function just like this. Seism say the all after 18% will be in this row. It means if we monitoring about the creep rate, you can find the creep rupture lifetime. It's very important. This is a best extensometer. Yeah. So almost the same function. Just like this. So after that, we almost 20 years ago, we developed the new type of sensor, tier sensors. And the tier sensor, this is the imaging. And where we use the steel rod, insert the ground. So for shallow and slope failure is very effective. So others we use other sensors, of course, very important, so water contents. So at the same time, so we carry out the monitoring after that. And another keyword is multiple sensors. For use many sensors, if sensor is the cheapest, we can use it many sensors at the largest slope. Of course, sometimes our specialists tell us, but set up the sensor in here. But if one sensors cannot find the exact precision. If the setup in here, after that, maybe destroy happening in this area. So it's a big problem. If so, multiple sensor, and we check the room monitoring. If this area gave the failure, we can catch this phenomena. Yeah, after that, of course, after that, I will give the another case study will be carried out in Brisbane, Australia. You can see this is a typical landslide landslide where we use because every year there's a slope moving, never stop. So after that, I go to this field and set up the 5 sensors here, just 1, 2, 3, 4, 5 in here. Yeah. So after that, we give some imaging. So for monitoring, we can get the movement and put some image in my brain, but the early warning or find out the threshold is, I think, the control the risk, manage the risk become very important. The first gives you an image only. There's sensor 1, 2, 3, 4, 5. The red color means they tilt to the slope direction. Now, blue-red means opposite, and reversed opposite the slope direction. After that, we'll give some image just like this. Here is a 2 weeks interval. The after 2 weeks, for the monitoring, we can feel this slope is moving or not. I think it's very important. It's the best one sensors. Our only checks the curve and the value. So gives this image is become very important. So multiple sensors has become very important. And after 2 weeks and after 2 weeks, that gives a large information about this landslide site. After that, we take the picture. In the top of the slope, you can see many cracks happening here. Yeah, many cracks happening here. But we never send out the early warning issue. Why? It never over our threshold value. Yeah. So what gives also, or maybe you will be asked some question. What is the time that we send out the volume issue based on the tiered sensors array? It's very important. Yeah. So last 20 years, we're carry out many monitoring in the world, especially in Japan, Australia, in China, and Taiwan. So we plot the failure case in this graph. The axis is tilting rate. The tilting rate is tilting rate, and the y-axis is the time until failure or stabilization. And for example, if the, of course, monitoring can measure the deformation in tilting, so will be tilt angle. For example, we use the threshold at the 0.1 degree per hours. You can check the safety where we get the 1 hour's escape time. But it's very large, very large scale, because so if checked use this point, we can get to 10 hours. If we use this, we can get 15 hours. So the detail information become very important. So we cater out the 3 types. The first is landslide, and the second is slope failure, and the third is a collapse. Of course, if according to this, for landslides, we can get much more time. It's for the slope failure, so we can get some time for escape. So this is average. It's very similar to an Markman grant law and the side model, side method. So it's very important based on the past research work and decide the threshold value. And another things will be introduced the multiple sensors monitoring. For this area, if you set up many sensors in here, so the whole of the area use the A0. The one sensor is just like this. The controls a small area, so they use the AN. This is average, of course. If one sensor is very dangerous, because maybe give out the four alarm. Four alarm means maybe attacks by animal and device bug and makes the mistake, makes a mistake. So for multiple sensors will increase the accuracy of the system. For example, you can see every sensor will be set up in here is very safety. After rainfall, one sensor and checks over the yellow level, gives some alarm, but the whole slope is safety. Of course, in this time, we'll dispatch the field engineer check the situation. So we'll give our much more time, prepare and check the detail and avoid the four alarm. The whole slope become the unstable. At that time, we'll send out the warning issue to the governor and the government. So conclusion, the single sensor maybe makes the four alarm because the warning issue can easily be affected by local movement, maybe by animal attack, etc., and many things. And multiple sensors that appropriate sensors interval for the multiple point measurement reduce the coverage of each sensors. Thus improving system accuracy, I think, is very important. This is tiered sensors case. Next, I will introduce our Seism, our laser vibration sensors. In here, I will be use the multi-point measurement of macro tremor and the seismic motion of slope using a small accelerometers. Of course, our purpose is very simple. And first, evaluation of geoground stability. And second, estimation of geoground velocity structure and the construction of ground model. And the third is estimation of depth contribution of support near of the ground. And next will be stability monitoring of slope and the rock fall. And estimation of slope failure location and verification of effect before the after countermeasure, such as ground improvement. So vibration sensor maybe can be used in many projects. Our pay attention to the bridge health monitoring. And second is a dam saver structure monitoring. and the GR disaster early warning and the mining dam safety management. And our sensor, maybe you note two sensors will be embedded our sensor unit. This is micro tremor sensor, and this is MEMS accelerometers. Three sensors will be embedded our sensor unit. This is micro tremor sensor, and the MEMS vibration sensor, and the accelerometer trigger sensors. Why? Will be save powers, because in the field no power saving. It becomes very important. In general time, if the sensor units keep the sleep situation, will serve power. And this is a very sensible sensor and for micro tremor. So why we should be develop the new sensors? As you know, micro tremor sensors very expensive. Very expensive. So we reduce the budget, reduce the cost. So at the same location or same field, we can use many more sensors to our monitoring, just like this. So the accuracy verification of the macro tremor mirrors uses more macro seism accelerometer sensors, just like this. And as you can see, this sensor is conventional sensor. It's very expensive, but it's very good sensor and a very good sensor. So at the ORB check the situation or accuracy, and we do the field test at the midnight, avoid the people's knife noise and the traffic noise. And this figure is a result. Is a Fourier spectrum of conventional macro tremor sensor, and you can see this is predominant frequency is almost 0.3 seconds. If I change the frequency, is almost about 3 hertz. It's very, very good result, because in Tokyo, the macro tremor sensor will be used or gets the predominant frequency are almost about 3 hertz. And the new sensors, where it checks, the new sensors almost gets the same result. Yeah, it's very good, very good. But our cost only 1/10 or 1/5. So it's very cheapest compared to the conventional sensor. Yeah. Another filter where we introduce another filter test. So where we use 5 set sensors at the small slope, the 1, 2, 3, 4, 5, and at the 5 sensor, nearby 5 sensor were set up as the conventional seismometer and checks the situation. It's very fortunate. After we set up, after we meet the earthquake happened in Chiba prefecture. It's not so far from our field. You can see the red color is the conventional sensors acceleration. Yeah, and blue color is our sensors curve. Is all matched, almost the same, and from north-south direction, east-west direction, and up and down direction. It's a very good result. Of course, you cannot further will be check the situation where you use the A50 and spectrum. Yeah, you can see from 0.1 second to 10 seconds, almost matched. Almost the same. Of course, acceleration is almost the same. And this graph will show the two sensors graph. This red one is number 1 is the top of the slope, and the number 2 is the bottom of the slope. You can see in this range, you can see it's become very large because the slope is very loosey. So the amplitude volume may become bigger. So we'll check the slope situation. It's good result. Of course, this graph will show the macrosweeper situation. It's very, very good result. Yeah, so we can use our new sensors at the actual slope failure and some health monitoring do the many things. The next case study will be introduced. We'll use the new sensor in rock fall and the rock collapse risk vibration survey. And in Japan, for rock and rock fall and rock collapse and risk vibration survey, in general, we use 2 or more sensors in here. Yeah, the one sensor should be set up with the bedrock. Bedrock is very is necessary. And another sensor will be set up to the rock mass is unstable. It's just in top of the rock mass. So we should be find the 3 parameters. It's become very important. The first is predominant frequency for rock mass. If the if the volume is under the 30 hertz, it means becomes unstable. And another very important parameter is about the RMS velocity amplitude ratio. If over 2, the rock becomes unstable, just like this. If the moving just like this situation, the movement, the RMS velocity amplitude ratio will become 1. Yes, over 2 is become a dangerous situation. After analysis, we use the attenuation constants. Of course, we're based our results come from acceleration, or we can calculate just like this. Yeah. After that, we'll set we jump this PPD, and for monitoring, 3 steps should be carried out, will be doing. The first, of course, after setup, the waveform will be output in our system, of course, by internet or transfer our data to Tokyo. And another is frequency spectral analysis, just like this. And the third was output the vibration situation. Finally, the calculation of the cumulative amplitude. And after we set up, the 1 set or 3 set of the vibration sensor in Hiroshima Prefecture in Japan. Here's Japan. Here's Hiroshima. Here's Shobara. Here's a field site. Field site. You can see from this picture, it's very unstable slope, very unstable slope. So for only by photo, maybe it becomes very dangerous. Very dangerous. In this site, we set about 3 set sensor here. So number 1, 2, 3. Please remember this direction. remember stairs. It's very weak crack. Yeah. It's fortunate after setup and a large earthquake happened in Japan, in Hiroshima. It says Kyushu is large earthquake happened in Japanese magnitude is MJ 6.4. The max system seismic intensity is over 5. It's a very large earthquake. Here's Hiroshima. Is far up from the earthquake epicenter is over 180 kilometers. Yeah. So our sensors catch the earthquake. Of course, for three sensors to catch the earthquake, and I will show the particle or orbit of displacement. Orbit displacement, you can see almost the same direction. This means orbit can find out the weak crack in the slope. Yeah. Another will be do the analysis. You can find the number one. The number one is bottom of the slope. The number three, the top of the slope. You can see the frequency is of course Fourier spectrum will be do plot just like this. This is lateral frequency. Yeah, this point is very important. And our predominant frequency. Yeah, is very important. And north-south direction and the east-west direction. And well, of course, almost the same result. This is ratio about the number 3 and the number 1 in north and the north-south and east-west direction. This is the peak, the rate. So we plot the result at the same graph. You can find the predominant frequency is very small, but the arm and velocity amplitude ratio is never over 2, is almost the 1. It means at this earthquake, the slope is moving, top and the bottom is at the same acceleration. But this is very weak. So the dominant frequency is very small. So ORB gives the result just like this. And RMS velocity amplitude ratio is less than 2, which judged to be safe. But the dominant frequency is a dangerous range. So because the judgment threshold is 30 Hertz is the unstable region. So it will consider this is because the ground structure becomes uneven due to the deterioration of the unstable rock mass, resulting in unstable structure. Finally, it is considered necessary to carry out a long-term monitoring. But what gives the result to the government is in this time is safe. So we save the money for government. Our government is very important about our monitoring results. And another things or another case study will be introduced is will be used to the expressway and the highway slope stability monitoring developed our seismometers. And it's very at a large scale monitoring or be carried on now. This is our challenge. Yeah, yes, our challenge. So if earthquake happen, this will be suppose the basis ground is just the green color. So the sensor will be set up the basis ground. If earthquake happen, will be use this sensor and measure the earthquake. Of course, will be reversed in this. For example, in here on this point will be used many sensors in the ground, the lowland, the soft layers. So we'll use this as the earthquake input, and this earthquake sensor, I'm sorry, seismometer will be get the output. So the relationship between the base ground and the surface ground is now becomes very important. And so ground vibration characteristic, of course, for example, the amplification, dominant period, are affected by the underground structure. So we'll be check the situation after that. And multiple point measurement on the ground surface and utilization of existing ground survey results is our purpose. And will be here, so much point measurement in mountain plateau and the lowland confirm the basement and the lowland side and the basement on the mountain side. So very important. Of course, or give some case study. So now for huge area, how one can set up our sensor? Where? How I can find the suitable site? Where is dangerous? Yeah, it's very important. The first, so the topography and geological characteristic of the study area should be evaluated first. In Japan, it's very easy to find out the geological map, and we can buy it. And slope classification map will be we can get from government. It's become very easy things. And for next, will be should find out where is the suitable site will be set up. Of course, we will use the drone and from get some macro topography and find out the dangerous. Next map is 100 years ago. The Kanto large earthquake happened. Many things. Many people died in here. This is 100 years ago situation. So this is now situation. So we can find some unstable slope failure happened here. I can find out, and at the same time we choose unstable slope, set up our tiered sensor and seismometer in here. And S1 is seismometer, and K1, K2 is tiered sensor. This is very dangerous because it's too sharp, is all about the 30 degree. Is very dangerous slope. After that, after setup, we check the situation. This is tiered sensor movement. After rainfall, after rainfall, we find the tilt sensor moving, but there's a slowing. So we'll be check the situation at the same time. And is fortunate. 1 year, so I catch the over 8 earthquake in this slope, or I will show the one result to you. This is not this is earthquake happened after we set up, and our sensor catch the earthquake data. And for frequency, we use the spectrum, Fourier spectrum, or plot the frequency to amplification, calculate by transfer function. Yeah, the red color is northeast direction, and blue color is east-west direction. And on the down direction, just we can find the peak about this result. They will pay attention to the northeast and on the down. This is east-west directions peak. And we carry out the calculation by supercomputer. Yes, it's very large computer. Of course, our first will be input the elevation distribution to the as a parameter, and of course the parameter will decide our right just in here or be jump it. And of course, just before I will introduce some soil property and rock property, or as an input parameter. And this is large calculation. So the FEM element, FEM will be over 10 million sediment. So this is result, or be plot just like this. You can see our monitoring site in here. But for the calculation, we can find the red color. Red color means it's unstable. Reason, unstable location. Unstable location. So it becomes very easy to find out where we can do the monitoring. Yeah. So the 3D seismal response analysis by FEM calculation. So for our monitoring sites, and you can see almost about the 3 hertz we can get almost the same result, just like this peak. And trough maybe is not so good because some we need more accurate information or because the input parameter to the computer. So the further investigation is necessary. Then finally, I will be introduce the another case study. The vibration and seismicity motion monitoring of the adjunct railroad structure behavior. As recent work carried out gets the result. As you can see, the large landslide happened 2 years ago. 2 years ago, and because the landslide, the deformation is a tonal shape changes, cannot use again, just like this. And nearby the railways in here. Of course, retaining wall becomes very important. So if the retaining wall becomes unstable, it's a very large program. This location is Toyama City. It's a very important railway railway road. So the collapse that should be not happening most. So it becomes unstable, and it's a big problem. And after that, we carry out the investigation. This crack happened here is very clearly, and nearby the railway and so passed from here. So we set up two sensors, the top and the bottom. On the two sensors, after train passed, we can get the vibration, and use the vibration where my judgment. After rain passed, of course, acceleration will be get. This is Fourier at a spectrum, and this river passed. Of course, this is top, or this is bottom, and this is top sensor, and almost half years we carry out the monitoring. We find there's no any changes, no any change for the no change for the natural frequency. So we give the result. This rating retail war is stable. There's no any problem. That gives the advice to the government. It's very, very good result. The conclusion, and there is no change in natural frequency over time, about the half years, and there is no tendency for retaining wall to become unstable. The government will be reduce the budget. Yeah, is fortunately after that a large earthquake happening here this year. So this year the Toyama earthquake, just our site in our monitoring site in here. Of course, we get the same. We monitor the earthquake, and the cloud just like this, and this is a peak, and this is a peak the natural frequency. The almost about the 18 hertz. This is ground on the natural frequency, almost about 8 hertz. This is north-south direction result and east-west result. Yeah, and your out and down result. So the finally result will be used right in the conclusion. The monitoring result of the Toyama earthquake, the natural frequency of the slope ground or in C direction is 8 hertz, and the acceleration amplification of the retaining wall and the by-transfer function is lost south, and down is almost 4.9 and 2.3. And the natural frequency range of the retaining wall is from 18 to 22. This result is close agreement with the natural frequency results 12 to 18 hertz for returning a wall observed during the train pass. The earthquake and the train pass get almost the same result, give the good advice to governor, and of course, and reduce the budget. Yeah, or from now on, we'll be do the monitoring, never stop. Yeah. Thank you very much. It's all. I finished. I'm so sorry. Is okay?
Yeah, thank you so much, Dr. Wang. So we can have some couple of questions from the participants. So dear participants, if you have anything, you can unmute and then you can start interacting with our speaker.
Mr. Lin, thank you so much for your presentation. I'm Dr. Pratik Negi from Calicut, India. I'm also working on geotechnical monitoring. I just have a question. Like, did it come across that some of your sensors installed over there got malfunctioned?
Multifunction. What's
Yeah.
it mean?
No. Malfunction.
Yeah.
故障。
Oh, yeah. Of course, the maintenance are very important. So we'll do the maintenance very well, or level for keeps a good condition. For example, our tilt sensor was set up in the Kobe city, over 10 years, but when we do the maintenance, never. We can use it continuous. I think maintenance is very important.
Okay. Thank you so much.
Yeah, hi, this is Bali. I
Yeah.
just have some Korean here. It's how it is feasible for general purpose. I mean, where you can use this is particular one site location, right? So how you can use. So in general application, you want to use this one. How it is? I mean, it will be applicable.
全然聞き取れないですけど。
Could you repeat the key issue?
Yeah, actually, this system, the early warning system it depends upon the site location. So the slope gradient and the slope angle and the geological conditions, and now people are using smart netting with sensors. So what was the difference this system and the smart netting system? If you have any idea, if you brief, it will be great.
Okay. Let me answer you on behalf of Dr. Wang. Well, my name is Tohata. I have been working with Dr. Wang for maybe 20 years for this early monitoring project. Well, actually, I'm not very sure about smart sensor networks, but for practical early warning of rainfall-induced landslides so number one, cost. There are many expensive but accurate sensing systems for important projects or for scientific project. We can use all those expensive sensors, but our client, local communities, they cannot afford high cost. So prices of sensors networks have to be reasonably low. This is called affordability. And number two, particularly in Japanese rainfall disasters, the time between the beginning of rainfall until the final landslide is only 5-10, not as long as 10. So let's say 8 hours only. So in the meantime, in this short time, we have to do monitoring, interpreting the data, and we have to make a decision. So system has to be simple. We cannot wait for, say, smart satellite image system come to the sky above the place. That's not good. That's not practical. And number three, we issue evacuation order when the rate of tilting is 0.1 degree per hour. This number is 100% empirical. So we have measured around 10 landslide events, and always the rate of tilting was greater than 0.1 degree per hour before landslide. So 0.1 degree per hour is empirical, but it's a lower bound and quite conservative. Probably geology is important, probably rainfall intensity is important, probably slope gradient is important. but we have only 10, 20, or 15 cases only. That number is too small for any statistic interpretations. So we take this lower bound as a conservative decision. Thank you very much.
Yeah, thank you so much, Tawada. Actually, it is a big challenge task we are facing in India, because to implement this early warning system, as per Government of India, we are planning. The government is planning to implement the early warning system in the mainly Himalayan regions.
Mm.
Yeah.
Dr. Bali, actually the system which we used is Dr. Wang's system at Kalimpong. You read the literature.
Yeah.
Yeah.
Okay.
Okay. So thank you so much, Sensei, for clearing this. And actually, just want to add to what Professor Tawata just mentioned. The system has been developed at Tokyo University under the guidance of Professor Tawata, and it has been like validated in different parts of the world, including India. And this is the most economical and reliable system which I have seen. So whatever the smart system you mentioned, I'm not aware of it because I'm actively involved in real-time monitoring of the landslides. So at different sites. So the reliability is a very crucial aspect, and monitoring is not a kind of, it is a site specific. You have to design it, where to monitor, how to monitor, and there are many factors do come. So we cannot have a kind of prescription sort of thing. This is the sensors, this is the unit, and you just buy that and put it up. It doesn't work. Okay, so it has to go a lot of geological, geohydrological, geotechnical, geophysical surveys has to be carried out, and then only you have to put the instrumentation, and then only we can start developing the warning system. So just to add to what Sensei said, so
very extreme. Yeah, installation not so complicated as you say. So as you mentioned, very complicated, elaborate preliminary studies, but those studies can be very too expensive, and the local community cannot afford it. So we try to make the system reasonably inexpensive.
Yes.
Yeah, thank you, madam. Because nowadays the different companies are, started this early warning system by using smart lighting system. Like Terra Army, there are some companies like McAfee and Garware Technical Fibers. So they are started putting these sensors on the smart netting system in slope and rockfall protection.
I do agree, Dr. Reddy, but believe me, I have checked many of the systems, such systems from the companies as well, and they always say that what they are selling is like one of the best. But when it comes to installation, many of them have failed, and the results is not at all like conclusive. So maybe before selecting some system, we should always have a look at the literature, and then only we can get a confidence on our system. By just keeping the name smart doesn't make it a smart actually.
Yes, I agree with Dr. Pratik.
Well, excuse me, Dr. Wang's system captured more than 10 landslides, and the total number of installations has been was 1,000. So only 10, 15 slope failures out of 1,000. That's a typical number of landslide risk. And there are two mistakes in monitoring. One mistake is called false positive. False positive mistake means, say, sensors say, it's dangerous, please escape, but nothing happens. This type of mistake is actually accepted by the community because nobody is killed. But then another one is called false negative mistake. This is very bad because false negative means sensor does not say anything. Then suddenly landslide occurs and people are killed. And Dr. Wang's system never made a false negative mistake, but maybe there are several false positive mistakes. Thank
you, Sensei.
Correct.
Thank you, Professor. Thank you so much.
So any more questions from the participants? Dr. Wang, somebody wrote it about the cost of your system. Would you like to?
Yeah, I pay attention to the cost. I very difficult to tell you the exact cost because in Japan and China and in India is different. So you can give some your condition of the landslide. I will give some advice after that. Yes, okay. Of course, you can email to me, Professor Lima. Maybe after that, or tell me after that is okay.
Yeah.
Any problem.
Actually, so I think the extensometer, good extensometer is 10 to 20 times more expensive than Dr. Wang's instrument. This is the idea of cost.
So any more technical questions from the participants? So the lectures are recording and it will be uploaded in the ISMG TC220 YouTube link and also IGS YouTube link. Will be shared with all the registered participants, and the details of the speaker also I can share it with all the registered participants. Feel free to contact Dr. Wang, who is very active in responding back. So if there are no questions, I'll just proceed with it. Is that okay, Dr. George?
Yes, it is.
Okay.
I thank you very much, everybody, for attending this very interesting lecture.
So I personally extend my sincere thanks to Dr. Wang for immediately accepting my request, and also my teacher, my JSPS guide at Professor Tawata to joining this lecture. Also all our colleagues from Indian Geotechnical Society and others from other nations for joining this monthly lecture series. I suggest you to register it in that QR code given, so that you keep getting the announcements of the next monthly lecture. So whoever are interested in field monitoring in geomechanics, please, there is a LinkedIn page which Dr. George mentioned it in the starting, that you can follow, or you can also follow the YouTube thing so that, and register this, so that you keep getting the reminders and information about the every month lecture. So we'll be doing this monthly lecture series every Friday, preferably on Fridays on every month, third week. So please keep your slots open and join us, and we'll interact to share our knowledge. With that, I just close this session. Thanks to everyone. Thanks to Dr. Andrew, who is our chairman TC220, for actively, encouraging for this activity. And thank you so much. Special thanks to Dr. Wang.
Thank you very much.
Thank you.
Everyone.
Thank you.
Yes, thank you.
Thank you so much, everyone.
Thank you,
ma'am, for conducting this. Thank you so much.
Thank you so much.
We are closing.